Hello, everyone. First of all, thank you for coming. And my name is Angelos Biboudis. I work at Oracle at the Java Platform Group in Zurich. And in this presentation, we are going to see a little bit of the history of pattern matching in Java, a glimpse of the immediate future, and where we can go from there. So this presentation has many roles. So it can help us understand, it can act as prerequisite for today's presentation by Victor and Brian on serialization. If we take Brian's keynote today and we overlay that over this presentation, we will identify find the primitive that Brian talked about. So hopefully by the end of the presentation, we will identify the primitives and we will also understand the features that exist today and the intention behind the future of pattern matching in Java. So, and let's go through some examples. The next two slides, I'm going to show a world without pattern matching. And in the slide after that, like a slide that subsumes the same functionality with pattern matching. So let's see. The task at hand is to examine a colored object that, to pattern match over, to examine a colored object that holds an object and a color. And both color object and a potential object that can be contained in the colored object is point. Both are records, okay? And the task at hand is to examine the contents and run a query, okay? And we need to do that safely. So, and after making sure that our data, that the data that this record holds are of the type that we want, we will extract data and we will run our query. So the first thing, after we got our task, is to ensure that the object that we got is a colored object, okay? And then is to cast with a precise type. So instanceof will help us with this precise information through the VM, and then we are going to use the precise type in order for us to continue our coding. And then we are going to extract data. And, oh, well, I need to do the same for the contents because the static type of the first component of the colored object is object. So no one tells me that this is a point and I want to write safe code. So I will use again instanceof, okay? And then I will cast again, I will extract, and I will run my query, and I will be happy. And now good luck communicating that or debugging that or expressing my intent algorithmically. It's a little bit hard to communicate that. And now let's assume even if I'm sure everybody knows what pattern matching is, but if somebody doesn't know, we can simply read this, right? So if O is instance of colored object, and I want this to contain a point, and I want to get the x coordinate, and I don't care about the rest, and I care about its color. And now, if this shape, this pattern exists, this is not exists, is satisfied for the object O, then we have the control flow decision to follow the if and run our code. Okay? So this is very well readable. It expresses the intent of the developer. And it's also declarative. It's over the shape. What is a pattern? Let's try to define what is a pattern in general. So a pattern is a conditional query. It may succeed or it may fail. And then we are going to test for a shape. What is a shape? A shape can be thought as a collection of constraints, let's say, about the types. It's like it is really a collection of constraints. Like when we were pattern matching over trees or string sequences, it's like the constraint that A is followed by B, by C, by something else. It's like very similar. So we are going to apply a test, okay? Like instance of point. So here we express the constraint that we want. And if the test succeeds, it's going to do a few things. Firstly, it's going to perform a safe cast conversion to get the precise type that we want, as with point, like casting object to point. It will perform, like pattern matching, will perform 0 or more extractions of values, and then it will bind the result to local variables with names of our choice. Okay? And success or failure will be appropriately signaled through our code. So variables will be definitely assigned where we want them, and they will not be elsewhere. So we go from a constraint on types to control flow decisions, right? This is what actually happens. So pattern matching is a way for developers cast safely and avoid unsafe casts. And by expressing type-based constraints, they will get control flow decision. This is very important. And through this talk, we are going to examine these 4 things, essentially. Again and again, again. Each feature will enhance something or drops restrictions about something. And then we will see how those are the primitives in this case that Brian talked about in the first in his keynote. So pattern matching was added to the language over a long process, and pattern matching was steadily evolved. The language evolved and changed by respecting the past and getting ready to accept the future each time. This was done through Project Amber, and this presentation is like a vertical slice of what Gavin is going to present on Friday. So please attend his talk because pattern matching fits into a bigger picture. And we can count 6 JEPs here, which are about shield classes, switch expressions, pattern matching for instanceof, pattern matching for switch, record patterns, and unnamed patterns and variables, okay? And we count only the final versions. If we count like the preview versions, this number goes up. And up until the past, present, a little bit before the future, we will have improved our code significantly with pattern matching. And later, we can see how we may be able to improve our APIs as well. So, instanceof is, let's go back now, a little bit back in time. Instanceof is a very fundamental operation, okay? It is an operator. It has always been, from the beginning, an operator. It is an expression. It is a type comparison operator that assists us to take some decisions and be safe about what comes next in our code. So typically, an instanceof protects a cast conversion, okay, among reference types, among reference types only. That was from the beginning of times. So the typical idiom is that we have an object, or some type, and then we stored something there of some hierarchy, and then we say, oh, if O has it is an instance of string, then I can cast I can introduce a name, and then I can manually extract the data. We will see the same thing happening over and over again. Instance-of has been like the good old instance-of, has been traditionally defined as a protector of casting from the beginning of times, okay, between references. So instance-of was the first point for pattern matching to be present in Java. So this was introduced in JDK 16, and type patterns were introduced for the first time for instance-of in JDK 16, yes. So from that point onwards, instance-of has a dual nature. Type comparison operator, but also pattern matching operator. And what is a pattern? What is a type pattern? It is like this string S, okay? And it is not by accident that it looks like a variable declaration, because it is this exact thing that happens under the hood. This is exactly what this idiom was about. It was about storing safely the result of a cast with a name of our choice. And it is exactly the same. So instance-of is the precondition for safe casting. Please remember that until the end. And yes, so this S variable will be in scope accordingly, where it will be definitely assigned, because if the pattern matches, then we enter a scope, and then S will be definitely assigned there. And then we have a good, concise code. And let me take a small break to talk about the scope of S. Because if I wouldn't show you this, you would never observe that this is happening. This is so natural. So the scope of S, if O is instance of string of S, then S is going to be definitely assigned there in the if part, right? It's a Boolean expression, like false, true, true, and then S is there, definitely assigned. And but like for the negation of this expression, S is going to be definitely assigned on the else branch. And this is very, 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 very cool feature. And probably we used it, I used it and didn't know that this happened. Like, and this is magnificent. And yes. So let's switch topic a little bit now. To switch. In the beginning, we had a C-like switch. It had only one flavor. It was statement-based. It was limited, but of course it offered multi-way. Like the if then else, it's like an instance of it's like one way, let's say, because instance of queries about the type one way, and switch doesn't query about types traditionally or anything. And it has a very limited functionality, but it is multi-way. Case labels were limited to numerics, to some numerics, and string constants and enums. And this also happened gradually through the years. In the beginning, it was just byte, short, char, int, their boxes, enums, and string. And switch could not be evaluated, right? So we had only the statement flavor. And switch has been traditionally been used to describe state machines and tokenizers and character-based tokenizers and all of these things. And people didn't use it for, let's say, general purpose coding. It had fuzzy and error-prone control flow and default scoping. What does this mean? Default control flow behavior, the default control flow behavior was fall through. Okay? And the default scoping in switch was that the whole block is treated as one scope. So this makes things already hard to reason about. Code, yes, but also to reason about and read. And as we see in this example, since everything is one scope, we cannot redefine temp, like with the same name in another block. And in JDK 14, we take the first step to go from switch statements to switch expressions without changing the selector type. So no more fall through. And by using the arrow operator, which is something that is already very beautiful, and we should all start to use it. And what is very interesting is now that every case is able to return a value. So for each case, for each possible case that is going to be selected, I'm going to get a value, okay? This is very important, as we will see later for exhaustivity. Third bullet here. Each arm can produce a value, and of course, like a very interesting functionality is that we can also have a block there, and the block, after it does everything it does and executes all the statements and all the logic, it can yield a value. So now each arm like really returns a value. And for enums, we could also have exhaustiveness check. And I will keep that point for a single slide. Hopefully, I will tie everything together about exhaustiveness, which is a very powerful feature for safety. Then, we take a moment now to appreciate that pattern matching was introducing to switch in JDK 21. Now, switch works for all reference types and introduces pattern matching to switch. So I can have an object O that statically forgot its type, its object. So it's like a widened type from a long. And then I want to get a formatted string, okay? And I can pattern match over it. So I can say case integer I, type patterns again. I can use guards to further constrain the value. And I can return my string. I can also say I want to pattern match over any kind of integer without any guard. I can do that. I can pattern match over longs. No one prohibits me from doing that because we are talking about an object. And I also want to have an opinion about null, which I couldn't have before with the previous switch. So I can write now case null, something else. And with default, I am able to capture all values of that can appear in this switch. Okay, so now we have type patterns in instance of and switch. Switch has been extended already, but there is another feature around that time, records, that we can also make it work with pattern matching in a very nice way. It was a very logical next step to do. So records were introduced in JDK 17, and their patterns were introduced in JDK 21. Okay? Records are transparent, shallowly immutable carriers of data. So transparent means that we can go back and forth from we can extract data, and we can also continue using our record without anything having changed there. The record will never change because it holds immutable data. So a receiver of a record will always, what they can do? They can always extract data. Like a record has a component list, and then it is very well specified that each component has an accessor of the same name, and then we call it, and then we get the data that we want. Very good citizen with extraction. So patterns can also play very well with this. So, and how it can be expressed, the pattern by using the same type. So we see in the first snippet, if object is instance of a box, and then we can continue further, as you saw in the first example, with type patterns. So string of s is a type pattern, int x is another type pattern. So we see already compositionality here, right? Patterns can be nested in other patterns. And of course, record patterns can be nested in record patterns that also contain type patterns. So what is the principle here? Because this shares, like the meaning that I show below is very, like we discussed about these things already. It's the accessing that is very important. So a record pattern knows how to automatically extract data if the user asked, since the user asked for them. So this was a perfect match for pattern matching, okay? So hence, record patterns are it's a very important feature for data-oriented programming and data introspection. Now we stay a little bit in the past with JDK 17, with sealed classes and interfaces that were introduced. So sealed classes are a feature that allow us to put a bound on the subclasses and the superclass to know how it is extended, right? So in the example below, if we have a sealed interface and we have 3 types that implement this interface, we know something about Celestial, right? The interface. We know what it means to handle all the cases of Celestial, all things that can be Celestial. So with record classes, we were able to express compounded types, composed types. I want a record of a point of product, Cartesian product of, like, you know what I mean. But with sealed classes, I'm building on top the notion of what enum had for values. But now it is becoming available for kinds of values. And enum, you could like have a number of cases, and then you could say, okay, now I handle all the cases of the enum, all the variants of the enum. And all those were like specific values. I handle all of them, I'm happy. But with types, I can do the same through sealed classes, okay? So I can say now, I handle all planets here, and all stars, and all comets. So it enhanced the notion of exhaustiveness. And this is the point that is like a personal favorite of mine. I don't know why. The patterns, this magnificent article, I highly recommend it, everyone to read it, because it explains all the core details of the most powerful feature of pattern matching, in my opinion. It talks about exhaustiveness and conditionality and reminder, and a small break again to talk about exhaustiveness. So what is exhaustiveness? It ensures, it is offering compile time safety for us. Bless you. And it is combined with suites it is ensured that one of the labels will be definitely selected. And I would like to remind you at this point that Java supports separate compilation. So allow me to state the facts. So this is what happens. If I write code that handles all the cases of my domain, I can be happy. If I don't recompile, if somebody adds a new variant, a new case, a new something, and they recompile the code, switches will be like compile time errors will be raised everywhere because exhaustiveness has done its work. Exhaustiveness will say, oh, this switch is not exhaustive anymore. You added a new kind of sealed of a class, like extending a new, like an existing interface, or an enum, or you change the type of a record, but of like a component of a record class. And that's great. What if we would use default? All switches would be happy, right? But there is a problem here. We lose type safety if we use default in an uncontrolled fashion. Because this feature is not about saving us writing defaults. It's about increased safety. So with all the compile time knowledge that the compiler has about all our domain, about the entirety of our domain, it can say your code, your switch is exhaustive or not at compile time, okay? At runtime, maybe we may have a novel type that has flown through our switch. How can this be possible? If somebody changed the model, but they didn't recompile the code. And if I had the default, originally, like short-circuiting exhaustiveness, maybe my switch at runtime, it would be perfectly valid. And it would handle a new case somehow, and then that would be problematic. So we should rely on exhaustiveness because it leads us to write safer code. And the compiler, for those novel types, will insert a synthetic default case raising a match exception if it encounters a new type, okay? And in this article, there is a very beautiful discussion about exhaustiveness, unconditionality, which is a stronger concept, and reminder, which describes all the remaining values that cannot be handled by a switch that can be exhaustive at compile time. And in JDK 22, in the previous iteration, we introduced unnamed feature holistically in the language, okay? So from the very beginning, the underscore character was perfectly valid, but also the intention to ignore stuff was also valid. But the character was there. So the best character to signify that we don't care about something. So there was a multi-year preparation through, like in OpenJDK, to transform gradually underscore, to take back underscore, the availability to use underscore. And in Java 8, compile time warnings were raised, and they were turned into errors in Java 9, and then only years later, we can reclaim this character to signify the intent of ours to ignore things. But what can be those things? So a holistic sweep through the language happened. because underscore, we can ignore things not only in patterns, but also with other occasions. As we said, a type pattern looks like a local variable. So local variables can also be declared as unnamed, but we may call a method that can have side effects or anything. And we want to clearly communicate that we don't want to give a name to this, but we still want to call the method. So unnamed variables were introduced in local variable declarations, lambda formal parameters, in the for loop, in exception handling, etc. And yeah, the same need arises in pattern matching. So we can have unnamed pattern variables now, symmetrically, fully with local variable declarations and the rest of unnamed variables. So if I have a case string s, and I want to ignore s, but I still want to handle the case, I can now use the underscore character and do that. Since I don't introduce names, it's perfectly safe to stack and include many now type patterns that do not introduce names in the same case. And this is very convenient. And if I want to elide so I elided the name. If I want to completely elide and remove the type and the name, I can also do that and use another kind of pattern, the unnamed pattern, which is single character underscore. So we add on the kinds of patterns, right? Type patterns, record patterns, unnamed pattern. And now we reached to the original example that I showed that is readable. And it says case color point of underscore. In the beginning, I think I was, OK. I wanted X, but I didn't want Y. So this is the other way around. So when I want to perform a query, OK? Let's dive into the future a little bit. Now, we are going to dive in the immediate future, something that is available today for us. So primitive types in patterns, instanceof, and switch were introduced with JEP 455. It is a preview feature in JDK 23. Please check this new functionality, and now I'm going to describe what this does. So there are multiple ways to present this, okay? And let's see what this means. We will start by me saying that this feature is mostly about dropping limitations around when primitives are involved in switch, instanceof, and patterns. But let me focus on patterns and switch for now. So before, we could switch over only certain numeric types, right? Byte, char, short, and their boxes, etc. Now we can drop that limitation, and we can pattern match over all types. And all selector types are now supported. We can drop another limitation about where primitive types appear. So we couldn't do case int I before. So now this is allowed and accepted by the spec and allowed by the compiler. And also there was another subtle limitation that actually limited a lot how people were doing data-oriented programming when they had components of records of primitive types. So primitive types were matched in patterns invariantly, which means that I could do a case box of int I only if the record was box of int of I. So this is what the word invariantly means, that there is no variance between the component types. Because with reference types, I can have variance. So my record in the beginning, remember, it was about string. I can ask something more precise, but I may have gotten an object or the other way around, and I can use and under the hood instance of ensures me casting and all these things that we discussed before. So I could say we dropped limitations, and if you're around after the end of the talk, I can show you the spec and show you, like here, we deleted parts in the spec, and we moved complexity in a very concise way somewhere else. But around instanceof and patterns, we dropped limitations. But let's dig a little bit deeper now, because primitives, we started from the high-level view of records and suites and what we can do, but there is a very deep connection with instanceof here. So there are some details that this feature helps us to avoid some unfortunate situation. What can be those unfortunate situations? Assuming that I have an int I evaluate it. The right-hand side is an int, the left-hand side is an int. I'm very happy. If I want to assign this I into a byte, the compiler tells me, because the compiler knows that this constant that has been used is it's big, and it cannot assign this value because there will be a possible lossy conversion from int to byte. Okay, but what about casting? I can cast an integer to a byte, and I will lose information there, right there. And the operation will succeed, and will be acceptable by the compiler. What about, and now I described the narrowing primitive conversion from integer to a byte. Okay, this is a little bit intuitive. What about int to float? If I use the same number, I can store it into a float, and incidentally, this number is the last integer continuously from 0 that can be exactly represented in float. After that number, I get rounding, up or down, roundings, if I want to store an integer to a float. So you see, I increment by 1, I try to store float, and then I lose information silently. So this is perfectly normal. Now I described a widening primitive conversion that can be lossy. And now we are starting to see the connections. So we need to go back a little bit on our principles and rethink what safeguarding conversions means. So we can devise manually all the manual tests with all these intricate details among all possible pairs between when we convert primitive to primitive. And then we can safeguard all our casts. Let's focus on the cast now, because cast is the fundamental operation for pattern matching, right? And I can do that. I can then safely cast and introduce names, and now we pattern match on the code that we saw before. But that is, and I can safeguard those casts against loss of information, like the magnitude that we saw before, or storing a big integer to a byte. But we can make safety first class and part of the pattern matching semantics. If we go back, we understand this pattern now. Safe, safe precondition of casting, something in the if that was before an instance of, that had the pattern that was translating with two instance of. So that's a job for pattern matching. So I can do the same with the instance of pattern matching, pattern operator, and introduce now top-level patterns. As we saw, this limitation was dropped, the second bullet from before. And this is a job for pattern matching. But if I drop the names, I need to get the same semantics to instance-of and really now use in the translation like now instance-of. So now instance-of safeguards, now with the preview feature, it safeguards casting against loss of information between all combinations of types that exist today in Java, references and primitives. And instance of, maybe I should have said that in the beginning, instance of conceptually has an opinion and safeguards against two exceptions, right? I should have said it in the beginning. I'm sorry, I say it now. Appendix. It has an opinion about null, and if a null reference will flow on the left-hand side, it will say false. So what's happening now? It protects us against NPEs. And it also protects, if we say it safeguards against casting, it safeguards us against class cast exceptions, which are already some form of loss. We lose the program counter. We go, like, an exception is raised, and then we lose, like, the normal execution of our program. And now with primitives, we also safeguard against magnitude, precision, range, sign losses. And there are many details around floats and doubles and -0 and -infinity and rounding up and down, and that byte with car have are both a narrowing and widening primitive conversion. Like I encourage you to play with these castings. Goosebumps now because I remembered when I did it. So it is a very interesting exercise for everybody to do. So we arrive now to the potential futures plan. And now we could talk for 10 hours about every of those bullets. And all of them are super exciting, okay? I mean, we have introduced already three like kinds of patterns, and we could talk today about constant patterns, about variable var args and array patterns, exceptions in switch, patterns in for each. When Valhalla gives us non-nullable types, we can introduce yet another another type for our type patterns. But all of those improve our implementation code. They do not improve our APIs. They improve our implementation code. These are all exciting directions, but today I would like to talk about improving APIs. And let's go through it. So what do I mean by this? Construction is a fundamental operation, right? It aggregates data. It composes a new colored object of a new point of a new, everything in one place. Deconstruction is an operation used to disaggregate our data. Record patterns orchestrate casting and what I showed you already, accessing of data, initialization, and everything, and also composes the same way with construction for record classes and record patterns. But what happened with classes? What fundamental piece are we missing here? And then if we make classes being able to be deconstructed seamlessly and compose deconstruction for classes as well, we can compose construction and deconstruction together. There is an occasion that we want to do it with records. Sometimes those have immutable data, but sometimes I want to extract, do something, reconstruct. I get a different reference, but I'm okay, I'm happy. So we're talking about this. So deconstruction of record classes, record patterns are derived from a record class. This is a snippet that we have seen already too many times for this talk, and I think I don't have a lot of time, so probably I shouldn't have shown it, but anyway. And the key part is automatic extraction, well specified. Record classes have this knowledge with the names, with accessors, with what happened with exceptions, and everything. And if we model our data with records, this is easy. If we model our data with classes, we miss the automated part because we extract data from our classes with getters, with various ways. And okay. So again, repetition, construction of classes is something that composes, that exists since the beginning of object-oriented programming. And then nothing changes here. What do we see? We see data flowing in as integers, integer, a type that describes a domain. And then it goes out as something bigger. So we added structure to two integers through point, okay? We have banded integer to integers into point. We added structure. And then as internal state, we store them as we want. Deconstruction of classes can happen with deconstructors. Which can be a new kind of declaration that knows, that the coder has on their disposable, that will encode this extraction part of data, okay? Because now we want to lose information, to go from a point and extract the data. Let's see the use side of this pattern. It's very familiar, right? Like now I assume that point is a class. It's very familiar. It's the same. So case point, int x, int y. I entered a p as the selector, and then something happened with pattern matching over a class that is called point, and I got out two bindings, and I continue. This is what happened with records, with record patterns. So one possible way is to introduce a pattern declaration that says that when I match, that this declaration matches, when it matches successfully, it will give me the initialization of these two bindings. And me, I know how I stored them, so I know how to give them back. So a pattern declaration with the same name as the class, like constructors. In this case, it's called point. It is matching a point, and it returns the variables to its binding. And this is the code that will run during pattern matching to initialize the bindings. So let's see an example of reconstruction now. I described you already what happens with records. So sometimes we need to reconstruct like a record class, do something, and then reconstruct it with a new kind of data that we have. But we are missing something crucial. We may miss something crucial. We may have a constructor in the class, in the record, that asserts certain invariants. In this case, the point needs to be on a two-dimensional plane. So what am I doing? Am I introducing with expressions for one, for the other, for a combination of the components, for all three, for what? And then I'm running individually the constructor that asserts and throws an illegal argument exception. So reconstruction of records can happen concisely, respecting those cross-component invariants, respecting the canonical constructor, making the construction and the deconstruction safer, the deconstruction and the construction now safer, by the upcoming Wither methods. So we may have a point, an existing point, that is called next location, and we say, I want to update all components, okay? And what really happens under the hood is that this is just a switch, not just. I mean, like this is a simplified version of what happens, but this is exactly my point. That it's a switch that is deconstructing, is doing something, and then constructing again by ensuring that things will be run. What the coder, the original author, wanted to ensure and communicate as invariant for point. And this will happen when we yield new point of x, y, z. And if I want to clone a point, so this is very like a simplistic example, but like this could happen. Like I can write point, clone point equals p with, and then brace, brace, and then it will deconstruct and construct with an empty body, but it's just like a very simple example, just to show that everything composes, and everything is hidden, right? Conditional testing, casting, automatic extractions, updates, nothing happened in this example. Construction that matches the extraction. Construction that matches the extraction. This is a very important point as well. We need to have a constructor with a matching signature with a deconstructor, and then we get this very powerful thing. And this is my pitch for today. Please, now, I'm pretty sure that you are fully equipped, and I will join you, because we all need to understand this new vision for serialization. Previously, for marshalling, we needed to extract data from an instance, okay? The old serialization was using reflection. But now, imagine that if we are able to go from our bigger domain, from our circle, to recursively down to the primitive, to our principles, which are primitive, the primitives in data, in our data world, then we can transfer them, and then we can reconstruct them in a safe way through matching constructors and deconstructors. Then we got something very significant. So if we have construction and deconstruction pairs all the way down to primitives, then we can get all these very important guarantees compositionally. Okay? So thank you for joining. We went through the past, present, and future of pattern matching in Java. There are very exciting directions for the future. It is a multi-year effort already, and there's plenty of interesting things in the horizon. We are now able to have recoverable abstractions. We are now able to safeguard all kind of cast conversions. And then introducing these features for classes with constructors and deconstructors, we can have recoverable abstractions there too. And then since we reached our principles and then we've built up, I think this connects to the keynote today very, very well. So thank you very much for joining.
All systems are nominal. Initialize Genesis sequence.